the other day. By the way, you guys can see the screen, right? The whiteboard? Okay, is it legible? Now that there's nothing on it. Um, so, um, is that coming through? Okay. A sample set is where we obtain characters from a subset, right? Of the population. Yes, now? And this marker's about had it. Why do we do this? It's cheaper, less time consuming. Right? Those are the advantages, right? Right?
Yep.
What's the disadvantage? Okay. I like the way you said it the first time, and it's due to extrapolation to the population. F of y x1, right? And this point here, f of x2, right? So if I blow it up here, I have something like this, right? Where this is x1 and this is x2, right? Yes, no?
Okay.
Yeah.
And I have these y values or these f of x values, right? Well, what if I want the data, the f of right here?
I like that her first day of school today. You gonna see how she's doing?
Somebody's got someone talking, which is fine, by the way. Let's say I want this data here, but I don't have that. I only have this and I have this. I don't have this data right here. I don't have an equation for the line. I don't have anything like that. So what do I do?
Estimate it somehow?
Exactly. So we got to do something, right? So we can do one of these, right? Just grab a number out of the air. What we normally do in a case like this is we interpolate. And we are going to do this later in the semester. We interpolate as if the graph, the function between x1 and x2 were a straight line. Why do we do that? Because we really don't have anything else we can do, right?
Good.
So we pretend it's a straight line and we approximate it, we estimate it by a straight line between these 2 points. Something funny?
Sorry, my girlfriend just woke up.
Oh.
It's like 2 feet behind me.
Oh, what's her name?
That's Kirsten. She can't hear
Kirsten?
you.
Oh,
Hold
really?
on, I can change it. If I think I can change it.
That takes all the fun out of it. Are we on speaker yet?
I think so.
Can you hear us?
Here, come closer. Yeah, you have to be over here.
Okay, everybody say hello to Kirsten.
Oh.
Hello.
Hello, Kirsten.
Hello, Kirsten.
You're famous.
Yeah. This is fun. Wouldn't be my first choice.
Oh, that hurts, does it not? Ah. Well, you're more than welcome to crash class.
Sounds
So, we got guys. Does everybody understand that if we treat this as a straight line, we can create a right triangle, right? And then we can calculate f of x by similar triangles. It's just a ratio of what's the best way to do this? It's just the ratio of the rise over run. So this distance divided by this distance equals this distance divided by this distance, right? By similar triangles. And then you just add whatever this is. You add that to f of x1, okay? But the bottom line is we are interpolating a point between the value of a point, the coordinates of a point, between 2 known points. Do you see that? We're going between them.
Yeah.
And usually interpolation is really accurate. Well, what's extrapolation then? Well, if interpolation is calculating the value, why is statistics not your first choice, Kirsten? That really hurts.
Oh, she walked away for a second.
Oh, probably because statistics is not her first choice.
Go
Anyway.
hide.
Well, thank you for putting us on. So, in extrapolation, if we use interpolation to get the coordinates of a point between 2 known points, what's extrapolation? We know the values of the points right here, right? So we're trying to get f of x for this value right here. Okay, so what we do is we extrapolate the known values, the known trends, and we pretend that they hold for values that are outside of any data points that we have. Which do you think is more accurate, guys? Extrapolation.
By a long shot.
By a long shot, right? Because you're making a lot of assumptions. Okay, we're making a lot of assumptions when we extrapolate. We're making the assumption that the curve, when it's extended into the unknown, follows the same characteristics as what we do know. Okay, interpolation, usually we have enough data that this error between the two real points is pretty small. In fact, when we look at interpolation for one of the continuous curves that we're going to look at in about a month, maybe 2 months, and maybe a month and a half. When we look at that, we're going to do some interpolation, and we're going to see that if we do that, our error is less than like 0.01% or something like that. It's pretty, the error that's introduced by interpolation is actually pretty small. Okay, so the problem with a sample set is that we are extrapolating data which is not as accurate as interpolating, but we don't have a choice because we're not gathering data from every single member of the population. Okay, and as we discussed on Thursday, right? When we do that, we can certainly end up with conclusions. We can draw conclusions that are not completely accurate. So, okay. Any questions on it? Okay, this is somewhat all review, correct? Can I get rid of it?
Hey, you wanted to know why statistics wasn't your first choice.
Ah.
Yeah, you.
Six.
Well, then why don't you want to try it?
Does anyone want to take a picture before I erase it? It's up to you guys. Totally up to you guys. Going once, twice. It definitely will be in the recording, right? Including Kirsten's rationale as to why statistics is not her favorite subject.
Oh, could you overhear that?
No, but I extrapolated. How's that for a segue? I extrapolated that was her response based on previous. How's that, guys? I'm kind of proud of myself, actually. Okay. Couple more definitions for you. An experiment in statistics is different than what you're used to. Okay? An experiment in statistics is, well, maybe it's the same. I guess on its face it's the same. An experiment is the process of gathering data. Well, that kind of sort of matches your expected definition of an experiment, right? Kind of, sort of? Yes, no?
Close enough.
Maybe. Go on. Okay, so kind of the tail end of running a chemistry experiment, right? This definition, right? Because it doesn't include the setup, all the beakers, all the gather this amount of this and that amount of that. So, but in the end, you're gathering data, right? In statistics, here's the difference, and it's a big one. I had to open the door. It's really stuffy in here. The act of gathering data is completely uncontrolled. And by uncontrolled, we mean that we gather data from members of the population. It does not matter who or what they are. Without. Exactly. Yep. So, campus bookstore, right? I forget what they call it. Something about the Commodore, I remember. Bookstore sells clothing, right? It's where you get your LCC hoodies and Toledo. Do they have Toledo hoodies? I don't know.
Very few.
Very few. Well, they should have quite a few. Anyway. Oh, actually, that's a great example. Okay. So, let's say you're the clothing manager, if there is such a thing, at the bookstore, right? So it's your job to figure out and stock what sells and kind of not as much of what doesn't sell, right? I mean, it's in your best interest to stock the shelves with your best sellers. I hope that's obvious. So, let's say you have absolutely no data from the past. So you're going to gather data from the population. The population in this case would be, what do you think?
Could either be just all students or students who are shopping.
Okay. All right. I guess the data that we gather would depend on the population, right? Because one of the questions we would ask, if it's all students, one of the questions we'd ask, if you shopped at the bookstore, what would you, right? While if it was customers of the bookstore, we would say, okay, what kind of clothing do you want? Do you want us to stock, right? So the question would be changed depending on the population. Do you see that?
Agreed.
Right. So, would you gather data from, let's say it's customers at the bookstore? Would you gather data from everyone that you could, or would you, depending on what we have, or I'm sorry, based on what we have, would you pick and choose who you're going to ask? It would be totally biased, right? If you went up to people that were, let's say they're well dressed, maybe seemed like they had a lot of money. Oh, we're going to ask them, right? Because they got a lot of dough and they're going to buy a lot theoretically if we stock the right items, right? Well, that's not uncontrolled, right? That's a controlled population, or you're asking, you're picking and choosing. Okay. In the truest sense of the term experiment in statistics, we don't pick and choose. The data is the data, whether we like what we're seeing or hearing or recording or not. Does that make sense?
Yep.
We do not pick and choose. Okay. I hope it's obvious to you that when people are involved in general, this is pretty hard to enforce. Do you see that? Has anyone bought a car lately from a dealer? Lately being ever, I guess. Anyone buy a car?
I did once 3 years ago.
Yeah.
Okay. So you went to a dealer, right? And you said, I need to buy a new set of wheels, or I want to buy a new set of wheels, right?
Well, that's totally how I said it.
I assume you are. I don't even know who's talking. Who is this, by the way? Who's talking?
It's me.
That's you, Brian. Brian. Okay. So, Brian, were you on the market for a the highest model that they have sitting there, a brand new car,
No,
60 grand kind of thing?
not even close.
Not even close. Were you in the market for a used car?
Yes.
Okay. I don't know if you if you noticed. Were there any well-dressed guys in there that were maybe 50 or 60?
No, I didn't really pay
You
attention.
probably didn't pay any attention. Well, I guarantee that if there were, they would get far more attention than you did. Why?
Sale potential?
Sale potential. Those guys are on commission, right? It looks a lot better if they sell a $50,000 car than, let's say, a $10,000 used car. Yes, no? Who they think. Yes. Is it correct? Yeah, probably. I almost bet money is correct. Is it right? Not by anyone that I respect, not by their opinion. It's just the way it is. True story. Well, I'm pretty sure it's true. I never looked it up. Back in I think the 1840s, maybe 1850s, somewhere in there. A young man was a student at Harvard University, and Harvard's in Boston, right? I'm pretty sure that's true. I think it is. If it's not in Boston, it's in the Boston area. I think Yale's in Connecticut. Is that right? Yeah. Right. Yeah. They are because the uppity types at Harvard, which pretty much is all of them, right? Harvard costs a boatload of money to go to attend. They refer to MIT as that trade school up the river. So, yeah, I know. It's like, what? You realize that all the technology you rely on comes from, or a good portion of it comes from MIT. Anyway, back in the 1800s, this young man was attending Harvard, and something happened where he died. I don't know if he got, he contracted common disease at the time, like tuberculosis, possibly, or if it was some accident. I think it was some accident, but I'm not sure. So anyway, his parents, who obviously were grieving, came to the school, and they talked to the president, and they said, "Well, we'd like to finance a building in our son's honor." And he was, I'm sorry. Yeah. He wanted. Yeah, well, that's what they wanted to do. And they were both in their like 50s or 60s. He wore a homespun, very old, very ragged suit. It was frayed around the edges, missing buttons, that kind of thing. She wore just a very plain dress, um, a very commoner kind of theme here. So they were obviously quite poor, and I think their son was there on scholarship. That's how they could afford it. So President of Harvard looked at him and said, a building, to finance a building in your son's honor, that's going to require a very, very large financial commitment, and it's probably well outside your means. It's probably too expensive for you. And they pressed the president to give him a number, and I don't know what number he said. Maybe $100,000 back in their time, right? We're talking 1800s dollars. So when they heard that, the woman looked at her husband and she said, "Well, if that's all a building cost, why don't we just create an entire university in our son's honor?" You know what their name was? Stanford. They are the founders of Stanford University in California.
Is that real?
It's supposed to be a true story. And I'm reasonably sure if you Googled it after class, it's probably very true. Something like it. They were turned away from Harvard because, again, it was a controlled experiment, sort of, and the president didn't get the right data because he made assumptions. So always be careful about judging a book by its cover, right? Because a lot of times you'll be dead wrong. So that's an experiment, right? Now, the data that we get, and we said this before, could be numerical, or what's the other type of data? Do you remember? Categorical, right? So examples of numbers, GPA, right? That's a number. Roll of a die. We talked a little bit in digital logic about some of the other things that could be numbers. Voltage, right? Current, resistance, power. Horsepower, right? If you're into cars, right? What's the horsepower of that Chevy over there? So horsepower, if you're again into cars, engine size. Guys, there's an entire, pretty much infinite number of things that we could put up here. Okay. Now for numbers, there are two types, two general types. Okay. There's discrete, and there's the other type is continuous. What does discrete mean? If we get data that is considered discrete, what does that mean? Okay. Yeah. There's a finite number of values, possible values. I'm running out of room, so I'll just finish up here. Possible values between two bounds. Or it's an infinite sequence. It can be represented by an infinite sequence. And you say, well, an infinite sequence, it can go from 0 to infinity or negative infinity to plus infinity. How in the world could that be discrete? Because that's not a finite number of values. Well, careful. The obvious examples of a discrete data would be something like if you roll a die, right? That's the obvious example, right? The numbers would be 1 to however many sides there are on the die. Okay? So 1 to 6 for your cubical die. What's a tetrahedron? Is that a 4-sided object? Tetrahedron? Is that right? Well, I don't know. There's 8-sided die, there's 10-sided die, there's 12-sided die, there's 20-sided die. So that's the typical example. Number of cylinders your automobile has, right? You might have a 4-cylinder engine under the hood, might have a 6. If you have a truck or something like that, there's a good chance it's an 8-cylinder. Okay, right? Okay, so if you have a tetrahedral die, it's going to be 1 through 4, right? Number of students in a class. Well, that's discrete, right? There could be only one person in the class all the way up to however many, what's the biggest number it can be? I don't know. Do you see that? Does everybody see that? Now, what if we ran an experiment where we flipped a coin 3 times, and we the characteristic is, out of those 3, how many times does the coin turn up heads? Well, I hope that's, if you think about it, I hope you come to the conclusion, well, that's discrete. None of the tosses could be heads, in which case is 0. 1 could be heads, 2 could be heads, 3. So, right, 0, 1, 2, or 3, right? Those are the possible values, right? Do you see that?
Yes.
On the other hand, what if we ran a similar experiment, except we're going to count the number of heads that we flip before we get the first tails? Okay. Well, I hope the lowest value we would record is 0, right? If the first flip turns up tails, well, you got 0 heads before you got a tails, so it's 0. If the first one heads, second one's tails, then the value of the characteristic would be 1. And if you did 2 heads followed by a tails, 2, right? Do you see that? What's the upper limit? What's the maximum value it can be?
Yeah, it could be anything.
Theoretically, it's infinite, is it not? Right? If you're having a really lousy day, right? And you just keep flipping heads, never get a tails, just keep flipping heads. Well, theoretically, it's up to infinity. Well, it's still discrete because you can represent the numbers 0, 1, 2, 3, all the way up to infinity. You can represent them by an infinite sequence. Does everybody understand this? Continuous, I'll write it over here. I have got to clean up my office. Anyway. I assume Kirsten lost interest in us.
She's working on anatomy.
Oh,
So-
she's a nursing student or science or something like that?
Nursing student.
Ah. That's nowhere near as fun as statistics. Anyway.
She said that might be true.
Continuous. If we have a characteristic that is going to yield continuous data, these are. This is the case where there's an infinite number of values between two bounds. Okay? If you are taking digital logic or have taken digital logic, this should sound really, really, really familiar to you. Yeah. It is. It is. Yep. Do you see that, guys?
Yes.
The signal equivalent is analog is continuous, digital is discrete. Okay. Examples of continuous would be voltage, right? Voltage, current, right? Current is continuous, yes, no? If we're measuring household current that a particular, well, any house draws at any time, we're going to get a range of values from really low to pretty darn high. How many values are there between those two bounds? Well, there's an infinite number. Okay. Horsepower of our earlier examples. Horsepower. We had this discussion yesterday in digital logic. I was was it Andrew that, I think Andrew said it. Andrew Nash, I think. He claimed, and I couldn't argue with him because he's right. He claimed that pH is not continuous. Is that a true statement? Most people would call it continuous because the pH of a solution can range from 0 to 14, and it can be any value between those, and there's an infinite number of values between those. And not quite so quick, as Andrew pointed out, right? pH is what? Negative log of the positive ion concentration. Do I remember that correctly? Yeah, well, not as long as for me. Anyway, uh, um, it's something to do with a logarithm. I know that. But at the molecular level, well, it's a measure of the ion concentration and the number of ions in a solution. That is a discrete quantity because you're counting things, and that is a discrete process. So Andrew claimed, and I can't argue with him, that pH is a discrete quantity. What's not discrete is something like length or width or area, right? Or time. Time to arrival, time between failures, things like that. Those are all continuous quantities. Okay? Does that make sense, everybody? Okay. And we've identified, discrete and continuous, and we're kind of sort of treating them differently. And the reason we have to do that, guys, is because the math that we're going to use for discrete data is different than the math we're going to use for continuous. And here's the reason why. For discrete data, we're going to use summations. Okay? We're going to use the summation operation to find the mean, the average value. We're going to use the summation operation to find the median, which is another type of average. We're going to use summations to find the standard deviation. All that kind of stuff we're going to use summations for. Okay? Continuous, if data is continuous, what that means is that it's going to look like this if we gather enough data. It's going to look very, very smooth, well, possibly not smooth at all, right? But it still is continuous, and to find statistics involving continuous data, we need to use calculus. We need to integrate. Okay? Does that make sense?
Yes.
So if you hate calculus, well, sorry. But we do need it to study the field of statistics. Okay, ready to roll into more stuff? Can I get rid of this? Absolutely. And you can do the opposite too, right? You could approximate continuous data with discrete values. For example, and we talked about this in Digital Logic, but most of you weren't in Digital Logic yesterday. If I ask you what the temperature outside is, temperature is clearly continuous, right? Well, what are you going to tell me? Oh, the temperature is 85 degrees. It's really sticky outside. Oh, you just gave me a discrete value, did you not? Is it exactly 85? Yeah, probably not. What is it exactly? Well, you're going to need a whole bunch of decimal places. In fact, you're going to need an infinite number of decimal places to give me an exact value. In other words, you can't give me an exact value. And I can't give you one either. It is continuous, but we approximate it we approximate things like temperature by quote unquote discrete values. Okay. More accurately, I would tell you that the temperature outside is, well, it's somewhere between 84 and 86 degrees, or somewhere between 84 and a half and 85 degrees, or something like that. That's how continuous data works. Here's the reason why. Let's say, okay, IQ. IQ is intelligence quotient, right? Right? It's arbitrary. What does arbitrary mean, by the way?
Not strictly unbiased.
Not strictly unbiased. Okay. Okay.
I was thinking more like unrelated.
Unrelated? Well, have you ever heard the term the arbiter said? You know, something? An arbiter between two parties? Okay. Yep. Yep. Yeah, well, kind of, right? An arbiter is somebody who helps make decisions, right? Is that decision right? I don't know. Is it wrong? I don't know. Um, Arbitrary values are values that you can argue with. And you probably ran into a lot of that stuff in calculus when you're dealing with functions. Let's arbitrarily say that x is 3. Well, you could have said, right? You ran into that in calculus, didn't you? Stuff like that. I guess not. Anyway,
All the time. Sorry.
if you ran into that, then you could have, although I wouldn't recommend it, you could have argued with your calculus teacher and say, I don't want x to be 3. I want x to be 4, because it is an arbitrary value. You just picked it out of the air. Okay? So, IQ is determined by an arbitrary test, right? They have intelligence tests, right? And a guy like Albert Einstein would probably fail an IQ test, even though he was obviously a genius, considered the smartest man alive. Those tests are geared towards a certain line of thinking. A musician probably, like somebody who's really famous, a classical musician would probably fail an IQ test. It's not their brain doesn't work that way. So anyway, I'll get off my soapbox now. It probably looks something like this, guys, where the middle is 100, right? You probably have heard the term that, the average person has an IQ of 100. If you're lower than that, you're not quite as intelligent as the average person. If you're greater than that, then you're a little bit smarter, if not extremely smarter than the average person, right? Do you buy that?
Yeah.
Well, would you the way I drew it is IQ continuous or discrete? Oh, it's totally continuous, right? Assuming if we got data from only 5 people, it would look like this. Okay. But if we get a data from a couple million people, then when we plot it, it's going to look something like this, okay? And we can call it continuous. So probability, we're going to get into this later, but I just wanted to show you something. You guys, between the entire class, let's say your IQ is maybe 100 or I'm sorry, 120 for the average person in this class. Just pretend, okay? So 120 is right here. Okay? Right here. To find the probability that a randomly selected person has an IQ of 120, what we do is we integrate the area under the curve between the two bounds. So like if we were interested in, say, I'm going to draw it on the other side, between 80 and, 80 would be here, between 80 and 90, what we would do is we would integrate this area. And that would be the probability that a randomly selected person has an IQ between 80 and 90. Does that make sense? You don't have to worry about the integration or anything like that. Just, does that make sense? It's the area under the curve.
Yeah.
Okay. So what's the probability that a person, randomly selected person, has an IQ of 120? It's a little bit of a trick question. Somebody said it. It's a point, right? What's the area under a point, guys? 0. Okay, so for continuous, we have to use integration over ranges for these calculations. Does that make sense? We have to do that because you can't, if you integrate under a point, you get 0. Okay. Exactly. You'd have to do something like that. And, if somebody says, well, what's the probability is 120, you say, well, 0. And after you prove your point, you're going to have a range because that's how continuous values work. Frequency. The frequency of a value is simply the number of times that value appears in the data. Okay. All right. So in our IQ example we did earlier, do you see that the frequency of 100 is probably the highest frequency in the entire data set? Do you see that? Okay. Mm-hmm. Yep. Okay. We can do a very quick. How are we doing on time?
20 minutes.
We got 20 minutes. Okay. Somebody's got to give me a 10-minute warning. Okay. We can do an incredibly quick experiment. Let's do number of classes that each one of you is taking. Okay. I'm not going to check. You can make something up. I don't care. Just make it believable. Okay. And I'll just go through. Okay. Brandon, how many classes?
5 classes.
You're taking 5 classes. You are a busy person. Brian Angel.
I got 3.
Who's next? Charles, how many classes you taking?
He said 4.
4? Okay. And who's next?
2.
Chris. Chris, you're taking 2?
Yeah.
The writing on my screen is tiny. Esteban, how many classes are you taking? I know you're taking at least 2. 5. Wow, another glutton for punishment. Kenny. How many classes are you taking, Kenny? Kenny might have stepped away. If you're talking, Kenny, you're on mute. Okay, we'll assign a number. Liam, how many classes are you taking?
I'm taking 4 classes.
And who's the last? Ryan?
I'm taking 3.
3? Okay. So, what are the how many are we going to assign to Kenny?
6.
4.
Just 4? Not 6. Oh my gosh, can you imagine that? Okay, let's assume 4. Okay. So what are the frequencies in this incredibly simple experiment? We start at 2, right? That's the lower bound. How many 3s we got? How many 4s? How many 5s? Is that it? Yep. Guys, these are all the frequencies. I don't think it gets any simpler than this, right? Now, if we plot the data, frequencies is on the y-axis. The frequency is on the y-axis. The value of the characteristic is on the x-axis. So we would start at 2, 3, 4, and 5. Okay. We have our choices. We can draw a little bar. Okay. What are the ranges of the frequency? Anywhere from 1 to 3, right?
Yes.
Okay. So 2 is 1. So we can draw a little bar like that. 3, we don't have to. We can just draw a point. Okay. For data like this, it's arbitrary how you do it. 4 had 3, did it not?
Yes, it did.
And then 5 had 2. That's what it would look like. Okay. You buy that? That's how it works. What's the sum of the frequencies? I get 8. How many people in the class? 8. The sum of the frequencies better add up to your populations. Oh, by the way, was this a population? Was this a census or data taken from a sample set?
Census.
Yep, exactly. Good job, guys. Real good job. Does everybody see that? I didn't mean it to be a trick question, but I guess it kind of was. The answer to the question depends on how we define the population. If the population is students taking this class, it's the census. If the population is students taking classes at LCC or even CSE students, and it's a subset. Okay. Yeah, very good, guys. Very good. So if it's a census, then whatever the sum of the frequencies better be how many data points you got total. Okay. The relative frequencies, or a relative frequency, is simply the number of the value of the frequency divided by the total number of values that we have. Does that make sense? You simply, in our data, you simply divide by 8. And you get fractions. That's the if you multiply by 100, you get percentages. Okay. So this is frequency data. To convert to relative frequency, you simply divide these by 8, right? So this would be 1/8. This would be 2/8 or 1/4, and this would be 3/8. Okay, those are the relative frequencies. All right. Does that make sense? Yes, no? Talk to me.
Yep. Yeah, it makes sense.
Okay. The value of the frequency. So this is the frequency. Okay. All right. If you yeah. Where'd my eraser go? Did I drop it again? Yep. This marker tray that it's got a ton of markers on it. Maybe that's why. I don't know. It always drops the eraser. Okay. We got to gather some data now for some example. Well, I can show you something real quick. A mode is the what quote unquote high point.
Quick question.
Go.
On your relative frequency, you don't reduce it?
We're going to find out that it makes sense not to reduce them.
Okay.
Because a lot of times we add relative frequency values. And if you keep them in the same denominator, fraction addition is much, much easier if you do that, right? Yeah. Yep. A mode is a high point in a graph. It is a localized high point. Okay. In calculus, you did graphs, right? Not graphs, but you found modes of a graph. You found maximum and minimum values, right? It's a local max. So if we have data that looks something like this, we have 2 modes. Okay, it's a local maximum. By the way, this type of curve, there's actually a lot of situations that this shape might apply to. One of them is years of experience at a certain company by the employees. Okay. The low number of years of experience, those are the new guys, right? Newer, right? Well, these are the older guys that have been around a while, the veterans. Okay. If it's a large company, a lot of times there'll be kind of a lean spell in here where they didn't do a lot of hiring. Okay. And that's usually based on economic factors. Okay. At NASA, this is typical. And actually, there's a third mode out here. This would be guys like me. Well, maybe a little older than me. I'm kind of in here with like 30-ish years. It's cyclical. Yep. Yeah. Mm-hmm. It is very cyclical. Okay. Big companies, yeah, like the automakers. If we plotted this data for the automakers, there would be like this lean period here. This could be approximately 10 years. So like something like, maybe 8 to 12 years, something like that. There's not a lot of hiring that took place. Anyone remember why? What happened about 10 years ago?
That was the recession.
That was the recession. And remember when they did the Cash for Clunkers program? Remember that? Well, the government, right? That was the government thing where they gave you $3,000 or so to trade in your old car if you bought a new one, right? Well, that created an artificial spike in the car sales, and the next year the car makers were really, really hurting because everybody that was going to buy a new car already did. So they had to do a lot of layoffs.
Turn in that year? Is that why they did?
I'm sorry? What's that?
Were they expecting the market to turn around in that year?
What, the government?
Yeah.
Brian, was that Brian?
Yeah.
Okay. Brian, this is probably going to come as a shock to you. Okay. I am somewhat cynical. Okay. And I have realized that whenever the government sticks its hands into the daily lives of people, everything gets totally jacked up because people do stuff they normally wouldn't do. The CARS program sounded good on paper, but again, for the automakers, they sold a boatload of cars in like 2010, 2011, I guess. But that was followed by 5 pretty lean years. So they just don't think things through.
Well, it didn't pay out for most people because it was like, if you didn't turn it in the first morning, like they ran out of all those rebates. There was a finite number of them.
Yep. That and I mean, okay, $3,000 sounds like an awful lot of money to you and I, but it's not enough money to get somebody to trade their car in if they're not ready. Does that make sense?
Yeah,
They're going to buy
a lot more than that.
Yeah. I mean, okay, it's a nice down payment, maybe. You still got to pay for the darn thing, at least the rest of it. So it didn't get very many people, and you can read some articles on it. In fact, I encourage you to do so. In hindsight, I don't think it got a lot of people to buy a car that weren't planning on buying a car. Does that make sense?
Yeah.
It maybe. Yep. Yeah. But like if you weren't ready, yeah, I mean, my wife and I we kind of drive cars into the ground. We just hang on to them forever. So like if a car is 5 years old, we're not going to trade it in. We don't want a car payment. Things probably already paid off. The Jeep's paid off. It's 7 years old. Am I going to trade it in? Why would I? It's running like a charm. Right? Anyway, okay, so we talked about modes. Oh yeah. How much time we got left, guys?
Oh, we're at 4 minutes.
Somebody forgot to give me a 10-minute warning. Okay. We got enough time to gather our data that we're gonna get a lot of mileage, pardon the pun, because you're gonna tell me the mileage on your cars. That's gonna be our data set. We're gonna use it for a lot of examples. Okay, so number of 1,000 miles, right? On 3 cars, 3 vehicles in your family. If you don't have 3 vehicles or you don't want to say, make something up. I'm not going to check. I will start it off, okay? Our data sets are frequently called X. X is the most overused thing in statistics. Okay, capital X, data sets are enclosed in curly braces. Okay, so again, I'll start it off. The Toyota has probably about 43,000 by now. It's, how old is that thing? It's 2+ years old, like 2.5 years old. So 43 grand on that. The Jeep has probably 137,000. You put on a lot of miles when you're out in the country. The truck has, I think it's like 103,000 because we don't drive it that much. Okay, who wants to go first? Go. Try not to give me round numbers like that. Okay, can we say it's 41,000? Okay. Okay. Who's next?
I can go next.
Go.
So my mom just got a brand new car, so that probably only has about like 16,000 miles on it. Not a whole lot. I don't really know how many hers is. My dad's
Again, I'm not going to check, Chris.
Right. My dad's car has about 143,000 miles, and my car has about 239,000.
Do you live in the country?
I do. I live in Medina.
Not the city, right? Medina Township.
Outside. Yeah, outside.
Yeah.
Yeah.
Okay.
Medina is just easier to say.
I know it is. I live in Spencer, so not too far.
Right. Yeah. If we were to say that, then I'd say Mallet Creek or York.
Oh, I know exactly where that is. Okay, who's next? Oh, but by the way, guys, for Chris's cars, notice who's got the most miles on their car and who's got the least. Just saying.
Oh, by the way, I'm not Chris. I'm Liam.
Oh, Liam, I'm sorry. I am so sorry.
It's fine. It's fine.
Okay, who's next?
Go with 88. 92.
Is this Chris?
Yeah,
is this Chris? Okay.
And 110.
Okay, who's next?
I can go.
Go.
I have 78. How many miles are in your car? Like 72.
This sounds like Brian.
72. And then like 350.
Oh, I love it.
That was a Honda.
I had a Honda that we gave to someone who ended up trading it in, which still rubs me the wrong way. Anyway, but yeah, it had like 260,000 or 270,000 or something like that when we gave it to one of my wife's friends. Okay, who's next?
I was gonna say now you ought to take the brands of all these cars and see which ones last the longest.
We could. Who's next?
8,000 miles,
Keep on going.
60,000, and
Keep on going.
22,000.
22?
Yep.
Okay. I'm going to change. Can I change the 60 to a 61?
Sure.
Just if it's not 61 already, it will be soon. Okay. Who's next?
I'll go.
Go.
125,000.
Okay.
107 and 94.
94. Who's got the 94?
That was my sister's.
Oh, she has the least amount of miles. Wow. Okay. All right. Who's next? Who hasn't gone yet? We have data from 6 of you guys plus me, so there's 2 that we don't have any data from yet.
I am currently trying to remember.
Just make something up.
Let's do 11.
Okay. Fairly new car.
Surprisingly, a 3.
Even newer.
And 58.
Somebody either doesn't get out of the house very often or has brand new cars all the time. Okay. Who hasn't gone? Does anyone know?
I wasn't really paying attention, but I'm assuming Kenny.
Kenny, you there? Ken.
Yeah.
Okay. Can you give me the mileage on three cars in your family? And if you don't, if you just make something up if you have
37.
to. 37,000. Go.
Yes. 140, 145 something.
Okay, that's good enough.
And 9.
9.
Yeah, my dad just
Okay.
got it.
Okay. All right. Cool. If you haven't written this down, can somebody take a picture of this and post it in the chat? Because everybody's got to write this down because we're going to get a lot of data from this. Okay. Obviously, we're going to plot it. And then we're going to find all sorts of wonderful values, including standard deviation, median, mode, and mean values. And we'll probably take it even further than that. Are there any questions? Okay.
On here.
Have a great day, guys. Have a great day.
You as well.